Hello, everybody. Today, it's Mr. Canfield. Whoa, almost got away with not saying who I was. How would you even know? Today, we study something called continuity and differentiability. So, continuity, back when I used to teach Algebra 1, when I lived in Maryland, continuity, we said, was a function is continuous if you can trace it with your pencil and not have to pick up your pencil. It's a really good working definition of continuity. So for example, let's say we have a function that looks like this. We would call that continuous. I'm able to move my pencil across it and not pick it up. Something like this, however, is not continuous. Trace, 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 trace. Ooh, I gotta pick it up. Now I'll put it back down. Trace, trace, trace. So we call this continuous. We'd call this not continuous. And continuity doesn't really care about how nice the curve looks. Like it could be like this. This is still continuous. But it's not enough for, oh, wait. It's a monster. It's not enough for us to say this like this. We actually have a really rigorous definition that we use for continuity. There's three things that have to happen for continuity to hold. And the first is that the limit as x approaches some value c of f of x has to exist. And c is essentially, we check all real numbers. So let's just draw some random curve here. Let's call this value over here, we'll call this c. So the first thing is it says that the limit as x approaches c has to exist. So if we come in from the left-hand side, go in from the right-hand side, we'll just call this L. So in this case, our limit is L. Okay, cool, yep, the limit exists. Part 2 says f of c actually exists. Does f of c actually exist? Yes, cool. Third one says, the limit and the function are the same thing. So the limit is L, the function is L, they're the same thing, check. These three things check off, this is a continuous function at x is equal to c. Here's the problem. I proved it's continuous there. I didn't prove it's continuous over here. I didn't prove it's continuous over here, or here, or here, 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 here. Yeah, that can take a long time. If we were going to prove it's continuous at every point, it would take forever. So in general, we focus on specific points to say, hey, is it continuous here? Or we'll say, find the points where it's not continuous. So we're going to do a bunch of examples today. We're going to talk through a bunch of different things and hopefully make sense out of it. So, you know what? I think this is actually helpful to read today. So it says, as our first one is really saying, as x gets closer and closer to c, both from the left and the right, we approach a limit, L1. Then, that's the first one. The second one says, f of c exists. That means the function is defined at x equals c. The y value at x equals c is existent, and it equals, we'll say, L2. The third one is only saying that 1 and 2 equal each other. L1 and L2 equal each other. So if any of these fail, it's not continuous. So let's go through it. So we're going to be finding if these are continuous at different x values. So we're going to talk about the x value 1 in this case. Is it continuous at x equals 1? Well, let's see. As x comes in from the left and as it comes in from the right, our y values are going to two different things. That means this first point here, they're not going to the same y value. So it fails on point 1. No, the limit as x goes to 1 of f of x does not exist. So let's look at part B. In part B, the limit does exist. The limit looks like it's this value right here. So in part B, the limit is that. So 1 is good. But what is f of 1? There's an open circle at 1. That means that f of 1 doesn't exist. And so even though 1, like this first one is true, this second one fails. And so this is not continuous at x equals 1 because f of 1 does not exist. I don't know why I wrote equals there. Dang. All right, let's look at C. So it's wanting it at x equals 0. So let's see. So we're coming from the left and coming from the right. Sure, the limit exists. So 1's checked. 2, let's see. Does f of 0 exist? Yeah, sure. Now 3. Are 1 and 2 the same number? Is the limit that? Yes. Is the function that? Yes. 1 and 2 are the same? Yep. It is continuous there. And you're like, duh, I can trace through it without picking up my pencil. I know. But we need to have this, we call this a rigorous definition. And the thing is, if you don't have all three of these things, then you can't trace it without picking up your pencil. And we want to make sure that we can say things more precisely than just saying, oh, trace through it without picking up your pencil. That's more of a colloquial definition. We want a way that even if you're not looking at something, you're able to look at it analytically, where we're plugging in numbers and trying things. All right, let's look at our next one. Let's look at D. Oh, now D is kind of weird, right? We've got this line and then whoop, we get this from a piecewise function. But in D, yeah, the limit's that, the function's that, and they're the same thing. Yep, D, it is continuous. Now let's look at E. You got to swoop, you got to swoop. The limit as x approaches 2 does not exist. This is not continuous. Done. Oh, wait, look at this one. The limit as x approaches 2 from the left and from the right, it's infinity. So for the first check, it's true. The second check, yeah, f of 2 exists. It's 2, it's right there. Or it's that dot right there, negative something or other. But for the third point, do the limit and the function get the same number? We got infinity for this one. We got negative blah, blah, blah for that one. Are those the same thing? No, it's not continuous. And sure enough, I can't trace this without picking up my pencil. Now let's look at this one. Wait, it's got an opening there. It's not continuous. And so we would need to say why it's not continuous. It's not continuous because f of, wait a minute, it's asking me for -2. It's not asking me for over here. I don't care about that. At -2, we're fine. At -2, wherever the heck it is, that's the y value, that's the limit, and they're the same thing. And then at this one, trace it without picking up my pencil. No, it's certainly not continuous at -1 here, if this is -1. Because the limit doesn't exist. So, example A is an example of what we call a step discontinuity. Notice how the function creates a step at x equals 1. I would actually call this a jump discontinuity, usually, but they're all just things that we kind of say informally. It's not that big of a deal. The only one of these that is important for us to talk about is B. B is an example of what we call a removable discontinuity. And this is normally called a hole. So normally that's what I'm used to seeing as well. Removable discontinuities, you might remember that from when we were doing limits. That's where you can usually factor the top and bottom and cancel something out, cancel out that place that's a problem. Okay. Hey, there aren't any pictures here. Okay, I'm going to tell you right off the bat, polynomials are continuous. Polynomials are also what we call differentiable, but that's getting ahead of myself. So all polynomials are continuous for all values of x. So A, is this continuous? Yes, it's a polynomial. B, is this continuous? Hold on, we don't know. It's not a polynomial, so we can't just say yes or no. Okay. And then, so the two right off the bat that we can say are continuous everywhere are going to be A and F. Now, F I didn't explain. F is not a polynomial. This is a transcendental function. This is 1 over e to the x. You know what? I'm getting ahead of myself. Okay. So, places where there's discontinuity, you're finding domain problems is nine times out of 10 what we're doing. So like here for B, when x is equal to 1, we have a problem. So we'd say x equals 1 is a discontinuity because at x equals 1, the function is not existent. But if we look at this graph, Look at this graph. Zoom back to standard. So you might notice that it doesn't look like it's discontinuous at x equals 1, but if we type in 1 there, we'll see y is equal to nothing. If we go to the table, we'll see we get an error at 1, because it can't be that. So this is what we call a removable discontinuity, because the numerator here factors to x plus 1 times x minus 1 over x, and the x minus 1's there, those cancel. So now we can plug in the 1 and find that the limit is 2. So the limit is 2, but the function doesn't exist. Hence, it's not continuous there. Let's see, the cube root of x squared plus 2x minus 4. Oof. Well, here's the thing. Odd root functions, you might not know this because we haven't talked a lot about this, but odd root functions actually never have domain problems. I can take the odd root of a positive or a negative. It's the even roots that are a problem. So odd roots, this is actually going to be all real numbers. We're good. I don't know if I've written that in this class before. This is continuous. We could say it's continuous on negative infinity to infinity. We could say x, or we could say f of x is continuous for all real numbers. It's just an upside down A. Upside down A means for all. It's a mathematical shorthand that we use when we're taking notes, because it's, instead of having to write f of x is continuous for all real numbers, I can just use it upside down A. It saves me time. I can also yawn while I'm talking. I look super professional. Hey, just to prove to you that this is good, see the zeros of this. Oh, this isn't even factorable, but if we look at this, x squared plus 2x minus 4 to the 1/3. It makes this weird looking squiggly thing. It's really funny looking. You're really funny looking, you know that? This doesn't have any discontinuities, but I don't know if I said this. The word discontinuity, it just means not continuity. It means discontinuous. It means it's not continuous somewhere. See how here it comes through, and then in between it's invisible, and then it's over here. Yeah, so this has some discontinuities. But we should look at this. So if I factor this, I get x plus 2 times x minus 3. Remember, I'm trying to multiply to negative 6 and add to negative 1. So that means that x is equal to negative 2 and 3, regular 3, not negative 3. Oops. So because of that, if I think about this on a number line, if I try plugging in something to the left of negative 2, so like, you can essentially make a sign chart out of this. So and then up here we'll have our x's. So here's negative 2. Here's 3. So let's try something to the left of this. Let's try negative 3. If I plug it in here, I get a negative. If I plug it in here, I get a negative. So a negative times a negative is a positive, and the square root of a positive exists. So we're good. Now what about at negative 2? At negative 2 we get a 0, we get a negative, so we get 0. The square root of 0 also exists. Now let's try something between here. Let's try plugging in 0. Any number between negative 2 and 3. I'll plug in 0, and I'll get a positive, then a negative. A positive times a negative is a negative. And the square root of a negative is a no. Does not exist. Let's try at 3. Here we get a positive, we get a 0. Positive times a 0 is equal to 0, and the square root of 0 is good. So we got good, good, no, good. I'm guessing that over here it's going to fail as well. Let's try 4. So I get a positive, I get a positive. My guess was wrong. A positive times a positive is a positive. Square root of a positive is a-okay. So the only places that we have a problem are in between -2 and 3. So I could say my discontinuities or discontinuous for -2 is less than x, which is less than 3. And I wouldn't include -2 and 3 because it's not continuous there. That's the negative way to put it. We could also say it is continuous, O-U-S, for x is less than or equal to -2, or x is greater than or equal to 3. We also use interval notation for this. For the first one, we could write that as -2, 3. And for this one, we could say -∞, -2, with a little u in the middle, and then 3, infinity. Wait, no, it's allowed to equal those. I should put brackets on them. So, let's see. That handles up to D. We gotta look at E. Okay, let's look at E. And with how much space I took up for D, I need to make sure I give myself enough room. So E says f of x is equal to cosine of x plus 2. Okay, this is the second video I'm filming in a row today, so I was like, oh, I'm taking so long. We're only 16 minutes in. This isn't bad. So cosine of x plus 2 over x minus 2. So all that's happening here is we are trying to find out places where it's discontinuous, basically where the bottom is 0. In this case, it only happens when x is equal to 2. Who cares what's happening at the top? So because of that, we'd say it's discontinuous at x equals 2. So, all right. And then the last one is 1 over e to the x minus 1. Well, e to the x, does this ever equal 0? Does e to the x ever equal 0? And you can try all you want. E to the x never equals 0. So it's continuous everywhere. And regular old e to the x is always continuous as well. So no, this is continuous for all. Alright. Now, let's see what's next. We wish to determine if piecewise functions are continuous. Do we? Do we wish? It is possible and usual that both pieces of a piecewise function are continuous. So let's look at this. We have two pieces here, right? We got the piece when x is less than or equal to 1, and we got the pieces when x is greater than 1. That's a polynomial. That's a polynomial. They're both continuous everywhere. But the real thing to check for is this, John. We want to make sure that the limit exists. We want to make sure that the left side and the right side equal each other. As long as the left side and the right side equal each other, we're usually good on piecewise functions. So all I'm really going to do is I'm going to say, hey, does 1 squared minus 3 equal 1 minus 1? If so, it's continuous. If not, we got a problem, because they switch at 1. So if I do that, I get -2. Here I get 0. So nah, dog. Not C at x equals 1. Now let's look at this one. What happens when we plug in -2? Well, let's see. We get -2 squared plus 3 times -2 minus 2. Is that the same as -2 squared? Let's do the hard one first. We're going to square this and then put the negative on it, so it's -4. Then we got regular 4. Then we got -6. Then we got -2. 4 minus 6 minus 2, is that -4? Let's see, that's -2 minus -2, it's -8. So 4 minus 8, is that equal to -4? Yup, -4 equals -4. It is continuous. Woo! All right, let's try this next one. -1, so 3 to the -1. That's 3 to the 1. Is that equal to 1 over C? in case it's not entirely obvious. No, it's not continuous there. This function, it goes off to infinity there. Or is it negative infinity? It'd be infinity. Anyway. All right, this is a classic example. When x is not equal to 4, what is it? When x equals 4, what is it? And here, when x is not equal to 4, we're fine. There's a couple things going on here. So first, let's check x equals 4. If I do that, on the top I get 4 minus 4 is 0. On the bottom I get 0. We get 0 over 0. But if I then go x minus 4 and we factor the bottom, x plus 4, x minus 4, then we wind up getting 1 over 8. So do we get 1 over 8 for this one as well? That's 1 over 12 minus 4. Pardon my sloppiness. Yes, we get 1 over 8. So at x equals 4, this is continuous. So the problem is this has another domain problem hiding in it, and that's when x equals negative 4 because of this plus 4 down here. When x equals negative 4, this is discontinuous. And so we would need to make sure we mention that. And so we have something called an interval of continuity. And so for this one, it's discontinuous when x equals negative 4, but at 4 we're okay. So what I would need to say is negative infinity up to negative 4, we're good. And then negative 4 to infinity, we're good. 4 was not a problem, because 4 we got 1/8 for both of them, but negative 4 was a problem. That's a tricky example. All right, so this is a classic AP question. It says, find the value of the constant k that will make the function continuous at the location of the rule change. Verify by calculator. Location of the rule change, that's not vocabulary that we tend to use in my class, and that's not any particular AP vocabulary or anything. That's just the way he's talking about it. So he's specifically talking about, I think I would usually call the switching over point from the 3x plus 2 to the 2k minus x. We're trying to find a value of k that makes this continuous, that makes these two equal each other. So we want this to equal this. That's supposed to be a k. And we want that to equal each other specifically when x is equal to 1. So it's 3 plus 2, that's 5. Here this is 2k minus 1. Uh-oh, don't know how to solve this. Add the 1 on both sides. Divide by 2. So when k is equal to 3, we have a continuous function. Whenever you see questions like this, it's all they're asking for. Super easy question if you know how to handle it. So like on this one, oh, okay, when x is 2, cool, I'll plug in 2 for x. So that's going to be 4k is equal to 2k minus 6. 2 squared is 4. So I'll subtract the 2k from both sides. Oh, we get k is negative 3 this time. Okay. Here's our last one. X is 1. Okay, so we get k squared minus 12 is equal to x. Plugged in 1 for x. Now this, I see a k squared. Oh, not x, sorry. Plugged in 1 for x, I got a k there. So k squared minus 12 is equal to k. We're going to have to subtract that k from both sides because the only way we have to solve this is if we set it equal to 0. Now I can factor it, I can complete the square, I can use the quadratic formula, but this factors really nicely. I get k minus 4, k plus 3 is equal to 0. So k actually can be two different numbers here. It could be 4 or negative 3. These are both possibilities. So that is where I'm going to stop this today. This should be enough. Let's see. Yeah, this should be good all the way up through number 6. It's a lot of questions though. So again, this in the homework, now we can do up to number 6. And in the next video, I'll take us through what'll help us handle the rest of it. And that's dealing with differentiability, which the short version of it is, does the derivative exist, and how can we tell just by looking at it? So hope y'all gained something from this. Have a good one. Bye.